So that result is this. Let f of xy be a continuous function and that satisfy a Lipschitz condition. That is mod of f of xy y1 minus f of x y2 is less than or equal to k times y1 minus y2 on a strip defined by this and minus infinity to plus infinity. If this x0 y0 is any point of the strip, then prove that the initial value problem that I am writing as IVP, y dash is equal to f of xy, y of x0 equal to y0 has unique or one and only one solution. Y equal to y of x on the interval AB. It's only this solution is there, one and only one solution. So this theorem is actually weaker condition than the Picard's theorem which we have discussed. Okay. So we are given a similar argument which we have did into the Picard's theorem, and with the some simplification is permitted by fact that the region under the discussion is not bounded above or not below. So in particular we start the proof in the same way as the series which we have defined into the Picard's theorem. The series which we have defined, let us write that summation mod of yn of x minus yn minus 1 of x plus mod of y0. That is no mode I have written. So this is the series y of x. So we have to prove that the series is convergent, or in fact is uniformly convergent. We shall show that. What is this ym? A yn of x is, we know that it is y0 plus integration x0 to x f of x comma yn minus 1 or t comma yn minus 1 t of dt. This is your ym. This is the sequence. To know, we know that this differential equation has a solution. That means this integral equation y of x is equal to y0 plus integration x0 to x f of x comma y of t or f of t comma y of t dt has a solution. So if I can say this equation 1 has a solution, it is equivalent to write the equation 2, which is the integral equation, as a solution, and the approximate solution for this is yn of x. So ultimately I have to prove that this series is uniformly convergent, because the partial sum of this series is exactly the ym that we have observed in the previous lecture. So with all these notes which we have already discussed in the Picard's theorem, we will use here and we'll prove that in the similar argument. So let us first define M0, M1 and M by this. M0 I am just saying it is mode of Y0. M1 it is a maximum of mode of Y1 of X. And M which is a sum of this M0 and M1. And we note that this y of x0 is less than or equal to m, and y1 of x minus y of x is according to the triangle inequality. This is y1 of x plus y0 of x, and as per this m1 is the maximum of y1 and m0 is mode of y2 y0. So that's why this is equal to m0 plus m1, which is exactly m. So we have y0 is less than or equal to m. We can say definitely by adding this m0 m1 into that, and due to this we have to write this. Now if your x is belongs to x0 to b, let's say your x is belongs to this. Now for this y2 of x minus y1 of x, if I take the modulus of this y2 of x minus y4, we know that yn is integration x0 plus y0 plus x0 to x f of t comma yn minus 1 of t dt. We know this. So as per y2 is y0 plus integration x0 to x f of t comma y of 1 of t dt, minus y1 is there, so it is y0 plus, or this is plus, so it is minus x0 to x f of t comma y of 0 t dt. So this is, we can write equal to integration x0 to x f of t comma y 1 of t minus f of t comma y 0 of t dt. So by property of this integration, we can write down this is less than or equal to x0 to x, and if I can take this modulus inside, mode of f of t comma y1 of t minus f of t comma y0 of t dt. But as per the initial value problem, we have dy by dx is equal to f of xy. Okay, so I can say d, or we can say that this first value, that is f of xy y1, sorry, not by this initial value problem, but we have assumed that this satisfying this Lipschitz condition, that means mode of f of x y1 minus f of x y2 is less than or equal to k times mode of y1 minus y2. So therefore we can say that this is less than or equal to x0 to x k times mode of y1 minus y2 dt. That y1 and y2 both of them are functions of t. So this is less than or equal to k times mode of m2 m, because of we have conclude that y1 minus y0 is less than or equal to m into integration x0 to x dt. So that is equal to k times k into m x minus x0. So this is the things we got. Similarly, what is y3 minus y2? So as the same argument, this is integration x0 to x f of t, y2 of t minus f of t, y1 of t dt. The modulus of that is less than or equal to by Lipschitz condition. This is k times x0 to x mod of y2 of t minus y1 of t. So this is, as we have discussed here, y2 of t minus y1 of t. That we can write y2 of y1 minus y2. So this is, we can say this is less than or equal to k times k square into m x0 to x t minus x0 dt. So that is equal to k square into m x minus x0 square by 2. And if you go into the in general manner, and in general, mod of yn of x minus yn minus 1 of x is less than or equal to k raised to n minus 1 m into x minus x0 power n minus 1 upon n minus 1 factorial. And this is the argument for all x which is in satisfying this interval x0 to b. The same argument can be given for the interval a to x0. So I can say that same argument is also valid for x is between a to x0, provided only that x minus x0 is replaced by mod of x minus x0. So we have in any case mod of yn of x minus yn minus 1 of x is less than or equal to k times k raised to n minus k m mod of x minus x0 raised to n minus 1 upon n minus 1 factorial. So this will gives you less than or equal to k raised to n minus 1 into m b minus a raised to n minus 1 upon n minus 1 factorial. So for each x, this is true for every x and for every n running from 1 to 4. So we conclude that the series, that is this series which we have here, this series is, we can write down less than or equal to, or absolute series of that we can write down less than or equal to that is now this mod of y0 of x plus summation n running from 1 to infinity mod of yn of x minus yn minus 1 of x is less than or equal. This quantity is already less than or equal to m. So it is m plus summation n running from 1 to infinity this quantity k raised to n minus 1 m b minus a raised to n minus 1 upon n minus 1 factorial. We can write down this. And what we can say, this quantity is convergent due to the comparison or ratio test. We can say that this is convergent. So by comparison test, we can say that this is convergent. So by ratio test, the series summation n running from 1 to infinity a power n minus 1 m b minus a raised to n minus 1 upon n minus 1 factorial is convergent. So hence this series n running from 1 to infinity yn of x minus yn minus 1 of x plus y0 is uniformly convergent. Let's say it is converged to, say it converges to y of x for every x is between the interval AB. Now, whatever the solution, because this series, its partial sum is yn of x, that means I can say that therefore the yn of x is converged to y of x as n tends to infinity for every x belongs to AB, which is uniformly. This convergence is uniform. Now, we have proved here, it is that the initial value problem has a solution. Now we need to prove that it has a unique solution. So for the uniqueness, we may assume that y bar is another solution. So assume that y bar of x is also solution of dy by dx is equal to f of xy with y of x0 is equal to y0. It also have a solution of this. So we will, our strategy, or we will show that yn of x will converge to y bar of x as n tends to infinity for each x is in AB. Okay. Why we can prove? If we can prove that, then we know that the limit of the function is always unique, and so this y bar and y is same. So that is our objective. If we can show that this yn sequence which we have, it's converging to y bar, then we are through, because the limit of the sequence is always unique, that we know. So as per that argument, y bar and y is same. That because of, we have to prove that it is uniqueness. So now we begin by observing that y bar of x is continuous and satisfy the equation, that is y bar of x is equal to y0 plus integration x0 to x f of t comma y bar of t dt. If A is the maximum of y bar of x minus y0, y0 is a fixed point, then for any point, then for x is in this interval x0 to b, we see that what is y bar of x minus y1 of x. As per the argument, y bar of x is this, and we know that y1 of x is y0 plus summation, integration x0 to x f of t comma y0 of t dt. So as per that argument, this is integration x0 to x f of t y of t y bar of t minus f of t y0 of t dt. So this is less than or equal to integration x0 to x mod of f of t y bar of t minus f of t y0 of t dt. Mod is there. This is by property of integration, and then using the Lipschitz condition, that is mod of this function with respect to y, it's k times x0 to x mod of y bar of t minus y0 of t dt. So that is less than or equal to k times a into x minus x0, because this mod of y bar minus y0, as per this argument we have taken, it is maximum of y bar minus y0. So we have k into a times x minus x0. Similarly, or we can have y of x minus y2 of x, which can be written as x0 to x f of t comma y bar of t minus f of t comma y1 of t dt. Again, by using the condition of Lipschitz condition, that is k times y bar of t minus y1 of t dt. And this we can write down as less than or equal to k square into a into x0 to x t minus x0 dt. So that is equal to k square into a x minus x0 square upon 2. And in the same argument in general, we can write y bar of x minus yn of x is less than or equal to k raised to n into a x minus x0 square by 2. So in the similar argument can be written, a similar argument result holds for your x is belongs to a to x0. So for any interval or for any x which is in this AB, we have mod of y of x, y bar of x minus yn of x is less than or equal to k power n into ax minus x0 mod raised to n upon n factorial. That is less than or equal to k power n into ab minus a raised to n upon n factorial. And this quantity is tending to 0 as n tends to infinity. So therefore, we can say that yn of x is converse to y of x, y bar of x, as n tend to infinity. We also have yn of x is converse to y of x, as n tends to infinity. And therefore, this y bar of x is same as y of x. So this, and this is true for every x in that interval, that is AB. And this completes the proof of uniqueness also. So in this theorem, we have proved that any set, any initial value problem, y dash is equal to f of xy. If f is continuous and f satisfies the Lipschitz condition, then it will have a unique solution is there. If you have any question, you can ask.